Hello everyone, this is chapter 4.4, which is the discussion on L'Hopital's rule. And L'Hopital's rule basically tries to get derivatives involved with limits and is the biggest tool in solving limits using calculus. So let's recall first some type of example we saw early on in Calculus 1 involving limits. This is a limit problem where that if you try DSP, remember that means just plug in the limit directly, we would try for DSP, the direct substitution property. Well, notice what we got on top is 3 minus 3, which is 0. Over on the bottom, we'll get 9 minus 3 squared, which is also 0. And we discussed that this was a indeterminate form early on in calculus. So it's indeterminate form 0 over 0. So what we're going to do is we're going to go back, factor, see if something cancels, and then try again. And notice the denominator actually factors as 3 minus x times 3 plus x. And the nice thing about that is that if you pull a negative out of this 3 minus x, you get negative 3 plus x, which is actually the same as x minus 3, and these cancel out. And since we're still in the limit as x goes to 3, now that we've canceled something, we have this now, we can attempt for DSP again after cancellation. And on top, we get 1, of course. And on the bottom, we get negative. Well, 3 plus 3 is 6, so it's just negative 1/6 actually. So let me just write that a little nicer. And there we go. So that's the answer there for this limit. Now we enter L'Hopital's rule. So, of course, first off, something that kind of always throws people off is the pronunciation of his name. So L'Hopital was a French mathematician, and for those of you that know how to speak French, then you'll know exactly what I mean when I'm trying to pronounce his name. The H and the S are silent, so a non-French speaker would say L'Hopital's rule to try to do the French accent justice. Otherwise, if you say L, Hospital's rule, that's not how you would pronounce his name. He would be offended. But anyways, he's not alive anymore anyways, but we just do that out of respect. So L'Hopital's rule says the following. It says, if the limit as x goes to a of a fraction of functions, f of x over g of x, is of 0 over 0 or infinity over infinity indeterminate form, kind of like the one above we just saw, then we can actually use this fact here, that the limit, the original limit we had, is the same limit as x goes to a, the same limit, x approaching the same number, that is, but now of the derivatives of each of the functions instead. Now, very often when you apply L'Hopital's rule, you can use different symbols for this equality. I often use LH like that to show that L'Hopital's rule has been applied. Some books use triangle, I think, is another way of doing that, writing that out. But LH is fine. You don't even have to put anything, but just at least explain to me when you've used L'Hopital's rule. So I think that's a fair way of doing it. But again, it's only applicable when your original limit is of these forms. So if it's not of that form, then it's a little trickier to move on. Anyways, moving on. So here I have two examples. Notice this is just the same as this one we did above, where we had to go back, factor, try again. But now we know that when you plug it in, right away it's of 0 over 0 form, so we can apply L'Hopital's rule. And remember, that's the same limit as x goes to 3, but now on top we can write derivative of the top, which is 1, and then derivative of the bottom is negative 2x, and then when you try DSP, you right away get negative 1 over 6, which is, wow, to say the least. This is one of the biggest mind-blowing applications of calculus to limits, which is right where we started off. So it's almost like we've gone full circle. Great. So now for this one, we've actually seen this a lot also early on in calculus. When we tried to especially find derivatives of sine and cosine, we needed this to prove the derivative of sine anyways. Also for cosine, I believe, as well. So limit as x goes 0, sine of x over x famously is 1. But we can see that clearly that when you plug in 0 directly, you get sine of 0, which is 0 on top, and then 0, of course, on the bottom. So this is indeed indeterminate form. So L'Hopital's rule is indeed applicable. So we have the same limit as x goes to 0, but now of derivative of sine, cosine, over derivative of x, which is 1. Now when you try DSP, you get cosine of 0, which is, of course, just 1. Wow. Wow. Really good stuff. So now we're going to take a look at a few more examples. There are a few cases that I haven't mentioned so far. We'll see those, but let me just kind of explain a little bit before we get there. A could possibly be infinity or negative infinity. A few other things is there are other indeterminate forms that are equivalent to 0 over 0, infinity over infinity, but require some finessing to get it of that form. And also L'Hopital's rule can possibly be applied more than once, as we'll see shortly. Because notice here, we got lucky that DSP worked after the first go, but for all we know, after using L'Hopital's rule once, we may still be in an indeterminate form, in which case we would just apply L'Hopital's rule once again. Okay, so now let's look at those examples right now. Right, so now we have 3 examples here, so let's see if we can apply L'Hopital's rule as needed. So if you try DSP right away, you get e to the infinity, which is infinity, and infinity squared, which is infinity. So this is indeed infinity over infinity form. So L'Hopital's rule is applicable. So in trying for L'Hopital's rule, let's see what we get. So we're still in the same limit as x goes to infinity. Remember, infinite limits are okay for L'Hopital's rule, as it turns out. Derivative of the top is e to the x. Derivative of the bottom is 2x. But then we're in the scenario where we get the same indeterminate form, infinity over infinity, when you try DSP. So we can apply L'Hopital's rule once again. So applying L'Hopital's rule once more gives us the limit as x goes to infinity of derivative of e to the x is itself, derivative of 2x is just 2, and now when you plug in infinity directly, you get e to the infinity, which approaches a positive infinity. Great. And what this actually suggests is that e to the x grows faster than x squared. In fact, e to the x will grow faster than any polynomial, any power of x that is. And with that being said, the quotient, if e to the x is on top of that and any power of x, will always approach infinity in the limit as x goes to infinity. If it's the reciprocal of that, then it will go to 0 because the denominator will approach infinity faster than the numerator in that instance. But here the numerator approaches infinity faster than the denominator is. Anyways, now this is a little different because for this one we see a different type of indeterminate form. And in fact, I kind of want to summarize here the different forms there are. So indeterminate forms, there are actually quite a few that are somewhat equivalent in some sense, meaning that L'Hopital's rule will still be applicable. And this is one. Notice when you plug in 0 from the right, you will see why that's needed in a bit. So when you plug it into this, we get 0 here, so that's going to be 0. So the indeterminate form here is 0 times ln of 0. Now, the reason why it's from the right is because ln only exists over positive numbers, not even 0. So the domain of ln is from 0 to infinity, well, with parentheses, so excluding 0 and infinity, obviously. So for that reason, you can't even attain negative numbers, so it wouldn't make any sense for the limit to be from the left. So we have to emphasize that it must be from the right, or else we can't even evaluate ln at those numbers. So it's kind of technical why that plus is needed. And yeah, so as x approaches 0 from the right of ln, this will actually get closer to negative infinity. So this is a 0 times infinity form. So the forms we've seen are 0 over 0, infinity over infinity. By the way, when I'm writing infinity in these forms, it could be plus or minus infinity. So the next one we'll see is 0 times infinity. And here this is of that form, even though it's a negative infinity. Again, these infinities mean plus or minus infinity, really. And, well, so I kind of want to say they're equivalent because one way to think of it is that infinity is like the reciprocal of 0. So you can think of infinity as 1 over 0, and 0 times 1 over 0 is just 0 over 0. Also, if infinity is a reciprocal of 0, then if you reciprocate top and bottom for infinity over infinity, you also get 0 over 0. So what this kind of tells us is not really that they're actually equivalent forms, but more or less that you can always, I guess the best way to phrase it is manipulate a limit that's of that indeterminate form to make it of another form. So in this case, if I wanted to make this infinity 1 over 0, I would have to reciprocate the part of the original limit whose limit was infinity. So if I wanted to write this as x over 1 over ln of x, that'll make this a 0 over 0 indeterminate form. But instead, in this particular instance, what I'm going to do is the opposite, actually. And you'll see why shortly. I'm going to reciprocate the first part, so that now, when you take the limit directly, this is actually of negative infinity over infinity, because 1 over 0 from the right approaches infinity. So this is negative infinity over infinity, which is an infinity over infinity form. So that's why I say they're kind of equivalent. And again, I explained that we could have wrote it in the 0 over 0 form. Okay, so now let's continue with L'Hopital's rule this way, and you'll see why I chose to flip the first one, not the second one in this particular case. So using L'Hopital's rule, we get the same limit as x goes to 0 from the right, I guess. I mean, leave some space here. Of derivative of ln of x is 1 over x. Derivative of 1 over x is negative 1 over x squared. And now you can see why I did that, because now we have no ln of x's now. And we can actually manipulate the inside before taking the limit. So we can just multiply the top by the reciprocal of the bottom. So this becomes negative 1 over x times x squared over 1, which is just x after cancellation, negative x. And as x goes to 0, this approaches negative 0, which is just 0 itself. Great. Now for this next one, this is a little different. If you plug in pi over 2, and this of course is from the left now, not from the right, like the previous one, and again, we'll explain why we need that in a second. Let's think for a second. Well, secant is 1 over cosine, and cosine of pi over 2 is 0, so this is 1 over 0, which approaches infinity in the limit. In fact, it's positive infinity because cosine is positive to the left of pi over 2. Okay. What about tangent? So tangent is sine over cosine, and if you plug in pi over 2, sine of pi over 2 is 1, cosine of pi over 2, as we just saw, is, 0. So this will approach 1 over 0, which actually approaches positive infinity in the limit. And the reason why we need this negative here is because if it approached from the right, then this would still approach positive infinity, but this would now approach negative infinity, because, maybe it's actually the opposite way. No, I kind of said it wrong actually. And you can see it if you wanted to view the graph of cosine, because cosine is really where this gets kind of messed up. Because cosine right here at pi over 2 changes but sign between pi over 2. So it's positive over here because it's above the x-axis, so here it's positive. And then below the x-axis, it attains negative numbers. So I spoke incorrectly earlier when I said this approaches positive infinity. No, I didn't speak. Sorry. So it actually approaches positive infinity from the left. There we go. If it was from the right, then it would approach negative infinity. So that's what I was trying to say. So since tangent is sine over cosine, to the left of pi over 2, which is this limit, this would approach 1 over 0, but positive numbers, so that would be positive infinity. So there we go. So that makes sense. But if it was to the right, which is where I was struggling on the explanation earlier, then it would be sine of pi over 2 from positive, sine is positive to the right of pi over 2, but then cosine to the right of pi over 2 would be negative now, so that would approach a negative 1 over 0, which is negative infinity. So in this case, it would be infinity minus negative infinity, which is infinity plus infinity in determinant form. And that indeterminate form, believe it or not, is actually not an indeterminate form that we look at in applying L'Hopital's rule. The one we do look at is infinity minus infinity, which is why this negative is needed, because, again, if this was positive, it would be infinity plus infinity. But since it's negative, this is actually of infinity minus infinity form. And that is actually, believe it or not, an indeterminate form where L'Hopital's rule can be considered. Good. So now what? Well, we want to get it in these forms. So really, to apply L'Hopital's rule directly, we don't want the weird forms. We want the two main forms that we discussed previously, 0 over 0 and infinity over infinity. So we're going to try our best to manipulate this so that it is of that form. Basically, what you want to do is you want to manipulate the inside of the limit so that it looks like a fraction, and then see if it's either 0 over 0 or infinity over infinity, and then you go from there. So the only way I know how to convert these into fractions is kind of what I've been saying earlier. This is 1 over cosine, this is sine over cosine. So in fact, right away, you can actually write it as 1 minus sine over cosine. just like that. Now, when you plug in infinity by DSP, you get 1 minus 1 over 0, so that's 0 over 0 form, and a 0 over 0 indeterminate form, well, L'Hopital's rule is applicable. So now we can use L'Hopital's rule in this form for this particular limit here. So this is going to be the limit as x goes to pi over 2 from the left of, let's see, derivative of sine, 1 minus sine is 0 minus cosine, so it's negative cosine. Derivative of cosine is negative sine, so that's this, okay, good. It's negative sine like that. Negative over negative, notice, is positive, so I can change those to positive. And then when you plug in pi over 2 from the left, well, on top you get 0, on the bottom you get 1, so this approaches actually 0. So far we're not really getting very many, I guess, interesting answers, or answers are just like 0 and infinity for these particular examples. But yeah, that's what I wanted to show so far. Now the next thing I want to show in the next set of examples we'll be taking a look at are more indeterminate forms. In fact, there are in particular indeterminate forms I want to show you that are of power form, and there are 3 of them. We won't be discussing all types, we'll probably just do 2 examples. That will be 2 of the 3. But the forms are of 0 over 0 indeterminate form, infinity to 0 indeterminate form, and 1 to the infinity indeterminate form. So I know it sounds kind of funny, but here 0 to the 0 is not an actual number. Notice, anything to the 0 is 1, but 0 to anything is 0. So is it 0 or is it 1? It's actually indeterminate, kind of like how 0 over 0 is indeterminate. So what this really means is that we have a limit of a function to a power of another function, and if you take the limits individually, the base function will go to 0, and then the power function would go to 0. And then you have the other cases for these ones. So here the base would go to infinity, the power would go to 0. Here the base would go to 1, but the power would go to infinity. And we'll kind of see that they're not as straightforward as you'd imagine them to be. Like this one for example, 1 to any power is 1, but if you have a form 1 to the infinity, it doesn't necessarily go to 1. And we'll take a look at an example of that form actually. So let's take a look at, like I said, 2 examples, one of these 3 forms. So let's see that right now. All right, so here I have these 2 limits that I wanted to show you that are of these exponential forms. Now notice when you plug in 0 here, you get 0 over 0 form. And here when you plug in infinity, you get a to the infinity, a is a constant here. That goes to 0, so this inside goes to 1. And then the power will go to infinity, so this is 1 to the infinity form. So they're different forms, so we can apply L'Hopital's rule. But we can't apply directly, we have to first do something to write it as a fraction. Now, the biggest, I guess, technique here, the only technique here, is to get the power outside of the power. And how we do that is by means of logarithms. In particular, I'm going to use the natural logarithm. So I'm going to call this limit y. There are different ways of doing this, but I guess what we can do is we can just call the inside y, and then take the natural log of both sides, like this, so that here we can apply the power rule of logarithms and bring the power outside of the log, like that. That's equal to ln of y. And then notice this is actually something that we saw already. We've actually solved this limit as x goes to 0 from the right. This was actually 0 from the previous example. But notice what we can do now is we can write this as a fraction if you want. And in this case, we wrote it as ln of x over 1 over x, and then we applied L'Hopital's rule. So, but we don't need to go through those. I'll kind of spare you the details because we already found the limit. So now what we can say is that the limit as x goes to 0 from the from the right of this, of x to the x, is the same as, let's see a way to reword this. So I want to say y, but we have ln of y. So how can we relate y to ln of y? One way of doing it is writing this as e to the ln of y. So basically I'm saying e to the ln of y is equal to y. So if you take both sides as powers of e, these cancel and you just get y. So e to this is equal to, well, e to this. There may be another way of doing that. I don't quite like the explanation there, but this method certainly works. But here, let's just kind of run through it. So what we end up getting is the following. Since e is a constant, we can just take this as e to the limit as x goes to 0 from the right of ln of y, which is x times ln of x. And we know this limit is, well, we found this to be 0. So the whole thing is e to the 0, which is 1. So the answer for this first example is 1. Now I know the explanation here was a little off-putting to say the least, but I think maybe a better way of saying it is this. If we take the limit of both sides of this, we get the limit of, well, natural log of what we were trying to find, and then this. So if this limit is y, kind of think of this limit as L or y or something, then if you take the limit of both sides, then we found out that the natural log of the limit as x goes to 0 of y is equal to the limit as x goes to 0 of ln of y, which is equal to this. And we know this is 0, so that means ln of this limit is 0. So that means if you take both sides as powers of e, then you get from here to here. You get e to this power is just the limit we're looking for. It cancels out the ln, and then you get e to the 0, which is 1. So I know that sounds funny again, but we're going to take a look at that exact technique here, because again we have powers involved. So the first thing I'm going to do is I'm going to call this limit, and again this I think was a little off-putting. So I'm going to do this. I'm going to call this limit L. I'm going to say the limit exists and let's call it L. Then we'll take ln of both sides. So ln of this limit is the same as the limit of ln of the inside. And that is certainly true because ln is a continuous function, so you can pass it through the limit. If you remember that from one of the limit properties we saw early on in calculus. We end up getting this, taking ln of both sides. Good. So now here we're applying ln only to get rid of this x. So if you bring the x out using the power of rule for logarithms, you get this. Okay, great. And now we have the limit as x goes to infinity of that. And now again, we want to apply L'Hopital's rule, so I want to write this as a fraction. And recall that the way we did it before is we kept ln on top and we moved this x to the bottom as 1 over x. So if you do that, then this would be the limit as x goes to infinity of, let's see if this works. So it's going to be ln of 1 plus a over x over 1 over x. Now, if this works, then taking the limit using DSP will give you an indeterminate form that we like for L'Hopital's rule. So either 0 over 0 or infinity over infinity. So let's see. When we plug in infinity on top, you get ln of 1 plus a over x, as x goes to infinity goes to 0, a over x goes to 0. So this is just ln of 1. ln of 1 is 0, so we get 0 on top. Okay. On the bottom, we get 1 over infinity, which approaches 0. So this is indeed the 0 over 0 indeterminate form. So now we can apply L'Hopital's rule. So I kind of skipped that above because embedded in this problem, we actually saw that in a previous example. So I spared you the details of L'Hopital's rule there. But here we're actually seeing it happen. So we have the same limit as x goes to infinity. But now derivative of the top, derivative of ln is 1 over the inside, but then by chain rule you have to multiply by derivative of the inside. So let's do that. Let's write 1 over 1 plus a over x times derivative of the inside. Derivative of 1 is 0. So this is just the derivative of a over x. Since a is a constant, it's the derivative of a, well, it's just a, times the derivative of 1 over x. Derivative of 1 over x is negative 1 over x squared, as we saw earlier, and that times a is negative a over x squared. Perfect. And over derivative of the bottom, derivative of 1 over x, like we just said, is negative 1 over x squared. So notice the negatives cancel, and if you multiply top and bottom by x squared, these cancel as well. So all we're left with really is just this, a over 1 plus a over x. So limit as x goes to infinity, like that, of a over 1 plus a over x. This is coming together really nicely, because now in the limit as x goes to infinity, this part here, a over x, goes to 0 like we saw earlier, and really this whole limit just is a. Now hold on for a second, because this is not our answer. This is the answer of the natural log of the limit, not the actual limit we're looking for. We want to find L, but we did all this work to find ln of L. And again, we needed ln to get the power down and manipulate it to be in the formula like for L'Hopital's rule. So now we've discovered here that ln of our limit is a. So then if we take both sides as powers of e, let me border this off, then these cancel and we get our limit L is e to the a. So that is our answer. And in fact, if you didn't notice earlier, this is something that we have definitely seen before. This is really just the definition of e to a power. So if it's e to the 1, then it's the limit as x goes to infinity of 1 plus 1 over x all to the x. And if this a was 2, then the limit would be e to the 2. So again, it just goes to show that even though it's of 1 to the infinity form, doesn't mean that the limit's 1. In this case, e to the a is only 1 when a is 0, which is something to think about. But yeah, that's all I'm going to say there. In fact, that really ends our discussion for 4.4. It was a lot. We saw a lot of really good examples. We saw a lot of variations of things. L'Hopital's rule is a very simple idea, but there are so many pieces to it as far as different ways you can apply it and different scenarios where you can apply it. So I hope I've given you enough there as far as piecing it together so that you can try problems on your own, and refer back to this video if you like, just to see when each of these techniques are applicable. So thanks for watching. I'll see you in the next video for more of chapter 4.